Controlling electrical power is a critical issue in an industrial facility. If controls in a facility lose electrical power, it may be impossible to operate systems and equipment safely. The safety of people would be jeopardized and equipment could be severely damaged. To avoid severe consequences during a power failure, critical systems usually have an emergency power supply system to provide enough power to allow equipment and systems to be shut down safely. A large battery, which is often called a station battery, is commonly the main component in a system that provides DC power in an emergency. To ensure that it will work when it is needed, maintenance of the battery and its associated systems must be performed on a regular basis. A primary component of many emergency power systems is the battery. A battery consists of two or more battery units, called cells, which are connected in series. A conductor is connected from a battery charger to the positive terminal of the first battery cell. Intercell connectors tie the negative terminal of the first cell to the positive terminal of the second cell. The negative terminal of the second cell is tied to the positive terminal of the third cell. The rest of the cells are connected in the same manner to complete the series circuit from the charger through each cell of the battery and back to the charger. The number of cells in a battery depends on the requirements of the loads it supplies power to. This battery has 24 cells. For identification purposes, the cells of a battery are numbered in sequence, beginning with number 1 at the positive end of the battery and ending with the last cell at the negative end of the battery. Another key component of a battery system is the battery charger. The charger converts alternating current to direct current. It provides a low-level direct current to the battery to maintain the battery at full charge. This particular charger also provides current to devices in the DC system, such as protective relays. One type of system arrangement can be explained using this simplified illustration. The illustration includes a source of alternating current, a battery charger, a battery, and a DC load. During normal operation, alternating current is delivered to the battery charger. The charger converts the alternating current to direct current and supplies it to components of the DC load, such as relays and indicating lights. The charger also provides a small direct current to the battery to maintain the battery at full charge. If for any reason alternating current to the charger is interrupted, the battery will instantly provide direct current to the entire load. It will continue to supply the load until alternating current is restored to the charger or until the battery is fully discharged. Now, while the main components of a battery system are the battery and the battery charger, a battery installation is required to include several safety-related features. One of these safety features is adequate ventilation. Batteries, when they're being charged, produce hydrogen gas, which is flammable and can be explosive. Proper ventilation prevents the accumulation of hydrogen. Because of the possible presence of hydrogen gas, smoking and open flames are prohibited in the battery area. Most DC system batteries contain an acid solution. In the event that battery acid should spill or splash on a worker, despite the use of protective equipment, a wash facility is required at every battery installation for rinsing and neutralizing the acid. To properly maintain and test DC system batteries, it helps to know the construction of the battery cell, how it works, and what can go wrong with the cell and why. Battery cells used in DC systems are typically lead-acid cells. The external components of a lead-acid cell include a container, which is often called a jar, positive and negative terminal posts, and a vent with a flame arrestor. The flame arrestor shields explosive gases at the vent from external sparks or flames. The internal components of a typical lead-acid cell include a liquid called electrolyte that's composed of sulfuric acid and water, conductive lead-based plates, and non-conductive separators. The separators insulate the plates from each other. Here the plates have been removed from the jar and partially separated to more clearly show how they're arranged. The plates alternate from a negative plate to a positive plate to a negative plate, and so on. The plates at each end of a cell are always negative, so there's always one more negative plate than positive. All the positive plates are mechanically and electrically linked together and connected to one of the terminal posts. The negative plates are also linked together and connected to the other terminal post. The most widely used cell plate design is a type called the pasted plate, although there are a variety of other designs. The pasted plate design uses porous lead compounds for the chemically active portions of the plate. This material is too soft to hold together by itself, so it's typically pasted onto a metal grid. The grid is typically an alloy that is either lead antimony or lead calcium. For this reason, some cells may be referred to as lead antimony or lead calcium cells. The chemical structure of the lead compound changes as the cell is charged and as it discharges. The electrochemical action in a lead-acid battery can be explained using this simplified illustration. The electrochemical action is a process that involves an outside source of direct current, the electrolyte, and the plates. Only two plates are shown here to make it easier to illustrate the electrochemical action. Initially, the porous lead portion of the plates in an uncharged cell is composed of lead sulfate and is gray in appearance, and the electrolyte is mostly water. The charging process and electrochemical action in the cell begins when the plates are connected to a charger and direct current begins to flow through the cell. As current flows through the cell, water molecules in the electrolyte are broken down into negatively charged hydrogen gas molecules at the negative plate and positively charged oxygen gas molecules at the positive plate. At the same time, electrons transfer from the positive plate through the DC circuit to the negative plate. Sulfuric acid that has been trapped in tiny pores of the plates is driven off the plates and into the electrolyte. This increases the concentration of acid in the electrolyte. The negative plate remains gray, but it changes into a pure spongy lead with a negative charge. The positive plate turns dark brown or black as it changes into lead peroxide with a positive charge. When the cell is fully charged, additional current will no longer change the plates, but it will continue to break down the water molecules to produce hydrogen and oxygen gases. These gases bubble up and leave the cell through the vent. This phenomenon is known as gassing, and it has several undesirable effects. It causes water loss, which lowers the electrolyte level. It also produces flammable hydrogen gas. If the gassing is violent enough, it may dislodge the lead from the grids. To minimize these harmful effects, charging current is kept at a relatively low level. When a load is applied across the cell terminals, the electrochemical action reverses its process and the cell begins to discharge. When the cell discharges, direct current reverses its direction of flow. Electrons transfer from the negative plate through the DC circuit to the positive plate. At the same time, sulfuric acid leaves the electrolyte and combines with the lead in both plates. This reduces the sulfuric acid in the electrolyte and increases the concentration of water. As a result, the negative plate changes from pure spongy lead back to lead sulfate, and the positive plate changes from lead peroxide back to lead sulfate. If the charging and discharging process isn't controlled, the electrochemical action in the cells will cause problems that can reduce the life of the battery. The ability of a battery to provide the backup power that's needed when it's needed depends on maintaining it at or near its rated in-service values. When talking about cell and battery voltages, it's common to refer to their open circuit voltages. Open circuit cell voltage is defined as the voltage measured across the terminals of the cell with no connected load. The open circuit voltage of a fully charged lead-acid cell is about 2 volts, regardless of the size of the cell. Since the cells are connected in series, the open circuit battery voltage is the sum of the open circuit cell voltages. For example, this battery has 24 cells, so the battery voltage is 2 volts times 24 cells, or 48 volts. Now, a common maintenance task for batteries is to measure the cell and battery voltages. However, the voltages are measured while the battery is in service. In other words, while the battery has a connected load. In-service voltages are different from open circuit voltages. The reason for the difference is that an in-service battery has a constant charge applied to it by a battery charger to keep the cells at full charge. This constant charge is referred to as a float charge. The float charge voltage per cell is slightly higher than the open circuit cell voltage. A typical float charge voltage is 2.2 volts per cell. So, the in-service cell voltage for this battery, measured across the terminals of one cell, should be 2.2 volts. And the in-service battery voltage should be 2.2 volts times 24 cells, or 52.8 volts. Now, in-service cell voltage is one indication of a battery's state of charge. In our example, an in-service cell at full charge should provide about 2.2 volts. As the cell discharges, the voltage decreases. When a cell is almost completely discharged, its voltage falls off rapidly to a value called its final voltage. The final voltage of a lead-acid cell is about 1.7 volts. The closer the cell voltages are to full charge, the more likely it is that the battery will be able to provide backup power when it's needed. A better indication of a battery's ability to provide backup power is its capacity. Battery capacity and cell capacity are the same. Capacity may be tested, but on a less frequent basis than voltage testing. The capacity of a cell is defined by its ability to supply a constant current for a specified number of hours. Cell capacity is typically rated in ampere hours. For example, a cell that's rated at 1 ampere hour when fully charged would be able to supply a current of 1 amp for 1 hour before fully discharging to 1.7 volts. Manufacturers typically rate cells based on an 8-hour rate of discharge. For example, this cell is rated at 200 ampere hours. This means it should be able to supply 25 amps of current per hour continuously for 8 hours for a total of 200 ampere hours. The capacity of a cell changes with different current demands. For example, if the load demands 35.2 amps from this cell, the cell will be able to provide 35.2 amps for only 5 hours. This translates into an ampere-hour rating of 176. So the cell capacity, or ampere-hour rating, is lower at higher discharge currents. On the other hand, if the load demands 20 amps, the cell can provide this current for 12 hours. This represents an ampere-hour rating of 240. So the cell capacity is higher at lower discharge currents. Another indication of a battery's state of charge is the specific gravity of the cells. The specific gravity of a cell is defined as the density of the cell's electrolyte in relation to the density of water. The electrolyte in a cell is composed of sulfuric acid and water. As a cell is discharged, sulfuric acid leaves the electrolyte and combines with the lead in the plates, decreasing the concentration of sulfuric acid in the electrolyte. So a test that reflects the concentration of sulfuric acid in the electrolyte will show the state of charge of that cell. That test is for the specific gravity of the electrolyte. The specific gravity of the electrolyte is the density of the sulfuric acid in relation to the density of the water in electrolyte. For example, 1 pint of water weighs about 1 pound. The weight of 1 pint of sulfuric acid is a little more than 1.8 pounds. When specific gravities of liquids are computed, a value of 1 is given to water. The specific gravity of sulfuric acid is 1.839. Any mixture of water and sulfuric acid, then, would have a specific gravity between 1 and 1.839. The specific gravity in a fully charged cell is typically around 1.210. As the cell discharges, the specific gravity of the electrolyte decreases because sulfuric acid leaves the electrolyte and combines with the lead in the plates of the cell. When the cell is recharged, the specific gravity increases because sulfuric acid is driven off the plates and back into the electrolyte. So the specific gravity of a cell provides another indication of a battery's state of charge and its ability to provide the required backup power when it's needed. In-service cell voltage, capacity, and specific gravity are all indicators of a battery's state of charge and its ability to provide backup power. And the value of each of these indicators is related to the value of the other two indicators. The relationship of voltage, capacity, and specific gravity can be shown using a simplified chart. The vertical axis represents values of cell ampere hours, cell specific gravity, and cell voltage. The horizontal axis represents time. The time is divided into discharge time and charge time. Separate lines are used to indicate changing cell ampere hours, cell specific gravity, and cell voltage. When a fully charged cell discharges, cell voltage drops gradually. Then, when the cell is almost completely discharged, the voltage falls off rapidly to its final voltage. At the same time, the cell's ampere hours of capacity decreases at a constant rate, and the cell's specific gravity decreases at the same rate as the ampere hours. When the cell is discharging, its voltage and especially its specific gravity change at a relatively constant rate. So a measurement of either cell voltage or specific gravity during discharge will give a fairly reliable indication of how many ampere hours of capacity are remaining in the cell. However, when the cell is recharging, cell voltage and specific gravity change at irregular rates. Cell voltage jumps instantly and then gradually increases till it matches the output voltage of the battery charger. Cell-specific gravity increases gradually as sulfuric acid is driven off the cell plates and mixed with the electrolyte. It may take weeks or even months for the sulfuric acid to thoroughly mix with the electrolyte and for the specific gravity to return to its normal value. Because cell voltage and specific gravity change at irregular rates when the cell is recharging, they are not reliable indicators of cell ampere hour capacity when the cell is recharging. Better indications are the voltage and current meter readings on the battery charger. When the cells first start to recharge, both voltage and current are relatively high. As the cells approach full charge, the voltage gradually increases and then stabilizes, while the current gradually decreases and then stabilizes. The cell and battery ratings covered in this part of the program are the traditional indicators of a battery's ability to provide backup power. If you understand the relationship of cell voltage, capacity, and specific gravity, you can compare rated values with measured values to determine whether a cell or a battery is good, marginal, or bad. A battery charger serves several functions in a typical battery system. First, it converts an alternating current input into a direct current output. Second, the charger applies the direct current output to a battery and controls the output in order to keep the battery fully charged. The charger may also provide some or all of the direct current to the DC load. The battery supplies the DC load only when the load exceeds the capacity of the charger, or when a power outage prevents the charger from providing direct current to the load. Chargers can vary in size and design, but most have some common components or features. An AC breaker is provided for connecting the charger to or disconnecting the charger from its source of alternating current. A DC breaker is provided for connecting the charger to or disconnecting it from its DC loads, which include the battery. A DC voltmeter indicates the charger output voltage being supplied to the DC loads. Normal voltage in this system is usually a little above mid-scale. and a DC ammeter indicates the charger output current. A battery charger will also typically have a switch or timer that is known as a float equalize switch. The terms float and equalize refer to two different charge voltage levels that may be applied to the battery. When the timer is off or at zero, the charger operates at a normal preset float voltage. When the timer is activated, the charger operates at a predetermined higher equalize voltage for the number of hours for which the timer is set. After the time elapses, chargers with a timer automatically return to the float charge voltage. Chargers with a switch must be manually switched to the float charge mode. In addition to the float equalize switch or timer, a potentiometer is provided for adjusting the float charge voltage. And another potentiometer is provided for adjusting the equalize charge voltage. In addition to all the components just shown, a charger may have a number of other components. Some chargers may have a pilot light. The light is typically on when there is an AC input to the charger. A charger may also have a ground fault detection system. The system on this charger uses positive and negative ground fault indicating lights. Both lights are typically dimly lit. If the positive side of the DC system becomes grounded, the positive light will glow brightly and the negative light will go out. If the negative side of the DC system becomes grounded, the negative light will glow brightly and the positive light will go out. This charger also has positive and negative ground test buttons. Each button, when pressed, will introduce a ground in its respective part of the system. The buttons may be used to check that the ground fault detection system and lights are functioning properly. Finally, a charger may contain a variety of alarms and relays, including a high voltage alarm and relay, a low voltage alarm and relay, and a power failure alarm and relay. The specific components can vary from one charger to another, so it's good to learn which components are included on the chargers in your system. In this topic, we looked at a typical battery system. We covered the components of a lead-acid cell and described the electromechanical actions that occur when a cell is charging and discharging. We discussed cell and battery ratings, including voltage, capacity, and specific gravity. If for any reason alternating current to the charger is interrupted, the battery will instantly provide direct current to the entire load. It will continue to supply the load until alternating current is restored to the charger or until the battery is fully discharged. As current flows through the cell, water molecules in the electrolyte are broken down into negatively charged hydrogen gas molecules at the negative plate and positively charged oxygen gas molecules at the positive plate. At the same time, electrons transfer from the positive plate through the DC circuit to the negative plate. Sulfuric acid that has been trapped in tiny pores of the plates is driven off the plates and into the electrolyte. This increases the concentration of acid in the electrolyte. The negative plate remains gray, but it changes into a pure spongy lead with a negative charge. The positive plate turns dark brown or black as it changes into lead peroxide with a positive charge. When the cell is fully charged, additional current will no longer change the plates, but it will continue to break down the water molecules to produce hydrogen and oxygen gases. When the cell is discharging, its voltage, and especially its specific gravity, change at a relatively constant rate. So a measurement of either cell voltage or specific gravity during discharge will give a fairly reliable indication of how many ampere hours of capacity are remaining in the cell. However, when the cell is recharging, cell voltage and specific gravity change at irregular rates. Cell voltage jumps instantly and then gradually increases till it matches the output voltage of the battery charger. Cell-specific gravity increases gradually as sulfuric acid is driven off the cell plates and mixed with the electrolyte. It may take weeks or even months for the sulfuric acid to thoroughly mix with the electrolyte and for the specific gravity to return to its normal value. A battery charger will also typically have a switch or timer that is known as a float equalize switch. The terms float and equalize refer to two different charge voltage levels that may be applied to the battery. When the timer is off or at zero, the charger operates at a normal preset float voltage. When the timer is activated, the charger operates at a predetermined higher equalize voltage for the number of hours for which the timer is set. After the time elapses, chargers with a timer automatically return to the float charge voltage. Chargers with a switch must be manually switched to the float charge mode. Safety is a serious matter. Electrical shocks and acid burns can be severe if the proper precautions are not taken. And the loss of eyesight is a very real possibility if the eyes are not properly protected. All required safe working practices should be followed to the letter. For example, before beginning your work, remove all metal objects, including rings, metal watch bands, metal necklaces, dangling keys, and any other personal items that could cause a short. Even a single cell, if directly shorted, can melt a ring on a finger. Protective equipment should be worn, including a long-sleeved shirt, an acid-resistant apron, insulated acid-resistant gloves, safety glasses or goggles, a hard hat, and a face shield. Some companies also require the use of acid-resistant sleeve protectors and rubber-soled shoes or a rubber mat on the floor. Also, you must know where the eye wash station is located before you begin working, so you won't have to search for it if you need it. And if you're not familiar with the eye wash station, read the treatment procedures before you start work, so that you know how to use it if you need it. If you need to use tools on the battery, they must be non-conductive, have insulated handles, or have all metal handles covered with a protective material. Only after you have taken the required safety precautions is it okay to begin work. Here is what a good fully charged lead-acid cell looks like. The electrolyte level is between the high and low level marks on the cell jar. The negative plates are thin and are a gray color. And the positive plates are thicker than the negative plates and are black or a dark brown color. One common cell problem is low electrolyte levels. Low levels are often caused by the small currents needed to keep the cell fully charged. The current changes water in the electrolyte to hydrogen and oxygen gases that leave the cell through the vent or the flame arrestor. Over time, a certain amount of water is lost. In general, lead antimony cells lose water faster than lead calcium cells. If the electrolyte level is low, water should be added to raise the level so that it's between the marks. Only distilled, deionized, or other approved water should be added. Tap water should not be used because it contains impurities, contaminants, or minerals that can shorten the life of the cell. Each cell is also closely checked for problems such as sulfation, cracked plates or plate growth, and hydration. If the electrolyte level drops below the top of the plates, sulfation can occur. Sulfation is the hardening of sulfur deposits on the plates. The deposits can prevent the cell from taking a full charge or from delivering its rated output current. Sulfation also occurs during the normal discharge of a cell. When light is shined on the dark positive plates, the sulfur deposits reflect the light, like sparkly glitter. Generally, the deposits are driven off the plates as the cell is charged. However, if the cell isn't maintained at full charge, the deposits will grow and become more difficult to reduce with normal charging. Another undesirable cell condition is a high electrolyte level. A high level may be produced by excessive gas in the electrolyte that forms from overcharging a cell. A cell that's undercharged will show different symptoms. It will have positive plates that are light brown or tan. If the cell were fully charged, the positive plates would be dark brown or black. Yet another undesirable cell condition is plate growth. Essentially, plate growth is the swelling of the grids. It is caused by grid corrosion. Corrosion results from the long-term effects of the sulfuric acid in the electrolyte on the grid. Plate growth can distort the plates, cause the grids and lead to break up, and prevent current flow through the cell. It may also cause the cell jar to bulge. In addition, plate growth will often push the terminal posts up, breaking the seals at the posts and allowing electrolyte to leak out of the cell. Finally, a cell may show a horizontal ring of white deposits around the plates and on the inside wall of the jar. These deposits are the results of hydration. Hydration is the dissolving of lead from the plates into the water in the electrolyte. Hydration occurs when a cell remains completely discharged for a period of days. The dissolved lead and water compounds, referred to as lead hydrates, crystallize and settle on all parts of the cell. Lead hydrates in the separators provide thousands of short-circuit paths between the positive and negative plates. The problem can worsen until the cell is no longer reliable as a source of backup power. Sediment at the bottom of a cell indicates that the lead is flaking out of the grid, possibly because of the continuous discharging and recharging or excessive and violent gassing. Too much sediment buildup will eventually short out the plates of the cell. A visual inspection for changes in a cell, such as hydration, sulfation, plate growth, and other visible characteristics, can identify problems in the cell. A battery inspection also includes checking the external condition of each cell. For example, plate growth can push the terminal posts up and break the seals around the posts. Cells with broken post seals should be replaced. The terminal posts are also checked for corrosion, which can increase resistance, reduce battery output, and keep cells from fully charging. Corroded terminals may need to be tested and cleaned. Each cell is also inspected for electrolyte that may have overflowed out of the cell. This would indicate that excessive and violent gassing has taken place. The electrolyte should be wiped off to prevent the acid from damaging the jar. A cloth moistened with a solution of baking soda and water will do a good cleaning job as well as neutralize the acid. Cells that are cleaned with unauthorized cleaning solutions may exhibit crazing, which is cracks in the cell jar. Crazing results from the chemical reactions of certain cleaning solutions with the cell jar. Cells are also checked for accumulated dirt and dust. Dirt and dust can create a conductive path from a terminal to ground, or between positive and negative terminals, causing the battery to discharge. Dirt and dust can also be cleaned off with a cloth moistened with a solution of baking soda and water. Finally, the flame arrestor should be checked for a white substance on its surfaces. The substance clogs the normally porous arrestor and makes it ineffective. A clogged arrestor can be removed and washed with clean, warm water. The arrestor is allowed to air dry in a warm location and then reinstalled. If the white substance reappears after 24 hours, the flame arrestor will need to be replaced. All battery work, including inspections, must be accurately and thoroughly documented. This documentation can be used to identify possible problems that may only be noticed by tracking changes over a period of time. These records are a key to scheduling prompt corrective action that may avert major failures. A cell voltage test is one way to determine if each cell in a battery is being adequately and uniformly charged. IEEE Standard 450 recommends checking pilot cell voltage once a month and all cell voltages at least once per quarter. IEEE stands for the Institute of Electrical and Electronics Engineers. Standards established by the IEEE are completely voluntary, although they're universally accepted and applied. Standard 450 also recommends that cell voltages should be checked with the battery charger in the float charge mode. The voltages are tested using an accurate, calibrated voltmeter, such as this digital volt-ohm-meter. The volt-ohm-meter is set to the DC volt position. The meter used here automatically selects the appropriate voltage range. These cells are lead-calcium, and on float charge should test at about 2.2 volts. The voltage is read to the hundredths of a volt and recorded. As usual, all required safety precautions should be observed. Since voltage testing involves contacting cell terminals, extra care should be taken to not short across terminals. The recorded cell voltages can be evaluated in several ways to identify possible problems. One way is to identify the highest and lowest cell voltages and determine the difference between them. The difference is compared to high and low cell voltage differences from previous tests. If there's a noticeable increase in the differences, an equalizing charge may be needed to raise the voltage of the weaker cells. Another way to evaluate cell voltages is to determine the average cell voltage. Then each cell voltage is compared to the average. Any cell that's below the average by a specified amount should be noted. The acceptable variation from the average is typically specified by manufacturer or company standards. Here, any cell that's 5/100ths of a volt or more below the average will be noted. A third way to evaluate cell voltages is to compare them to a critical voltage. IEEE Standard 450 states that prolonged operation of cells below 2.13 volts can reduce the life of the cells. IEEE Standard 450 also states that a cell voltage of 2.07 volts or below indicates internal cell problems and that the cell may need to be replaced. Low cell voltages by themselves do not necessarily indicate a problem with the cells. They do indicate that the cells have been insufficiently charged, which can happen for a number of reasons. For example, a low float voltage setting may not provide adequate charging current for slightly weaker but still good cells. Cell voltages can also be low because of higher than normal electrolyte temperatures. Higher temperatures increase the internal discharge of a cell and result in lower cell voltage. Higher than normal temperatures may be caused by internal shorting. If this is the case, the cell should be replaced. But higher cell temperature is often caused by outside sources, such as direct sunlight and space heaters. Steps should be taken to minimize the effect of outside sources. Another cause of low cell voltage may be poor intercell connections. Poor connections increase resistance and reduce current flow in the battery. With reduced current flow, weaker cells may not become fully charged and, as a result, will have lower voltages. The resistance from a poor connection can also cause heating. Excessive heating of high-resistance connections can melt the terminals. In extreme cases, poor connections can cause battery fires. Poor intercell connections are sometimes evident by visible corrosion at the terminals, but a terminal connection can look good and still not be good. One way to check connections is with resistance testing. Connection resistance is commonly measured using a microohmmeter. A recommended practice is to connect one probe of the microohmmeter to the positive terminal of a cell and the other probe to the negative terminal of the adjacent cell. This microohmmeter applies a 25 amp test current across the intercell connector and electronically calculates the resistance. It's a good practice to start taking resistance readings at one end of the battery and work toward the other end. Each microohm resistance reading is recorded. Normal resistances can vary with the size of the battery. According to IEEE Standard 484, a resistance reading for a new installation is suspect if the connection has a resistance that's 10% or 5 microohms higher than the average resistance for each type of connection. An example of a type of connection is all intercell connections. Another type is all inter-tier connections. For existing batteries, a connection is suspect if its resistance is 20% higher than the average that was established when the battery was first installed and tested. Or a connection is suspect if its resistance exceeds a manufacturer or company recommended limit. Intercell connections with unacceptable resistance should be cleaned, tightened, and retested. If the resistance is still unacceptable, the cell might need to be disconnected from the battery so that the connections can be disassembled and given a more thorough cleaning. The term specific gravity for a battery cell refers to the density of the electrolyte in the cell in relation to the density of water. A cell's specific gravity is normally an indication of its state of charge. Specific gravity is measured using an instrument called a hydrometer syringe. When specific gravity is checked, all required safety equipment should be worn, and all required safe working practices should be followed to the letter. To measure cell specific gravity, the syringe nozzle is inserted into the cell. The bulb is squeezed and released to draw a sample into the barrel. Some cells have a sampling tube. If electrolyte is taken from a sampling tube, the first sample is discharged into the vent well. Specific gravity isn't read from the first sample because the electrolyte in the sampling tube doesn't mix with and isn't representative of the rest of the electrolyte in the cell. A second sample is drawn for the specific gravity reading. While a sample is being drawn, the syringe is held vertically so the float doesn't touch the sides of the barrel. Enough electrolyte is drawn to lift the float off the bottom of the barrel, but not so much that the float hits the top of the barrel. If the specific gravity is high, the float will ride high in the sample. If the specific gravity is low, the float will sink lower into the electrolyte. Once the float steadies, the specific gravity is read off the scale at the surface of the electrolyte. The specific gravity reading here is 1.222. This is not necessarily the value that's recorded. Specific gravity is affected by temperature, so the reading may need to be corrected for the temperature of the electrolyte. Electrolyte temperature may be checked using a cell thermometer. Here the cell temperature is 68 degrees Fahrenheit. When electrolyte temperature increases, its specific gravity decreases because warmer liquids are less dense than cooler liquids. When the temperature decreases, the specific gravity increases. The normal or standard reference temperature for electrolyte is 77 degrees Fahrenheit or 25 degrees Celsius. To get an accurate specific gravity reading, the specific gravity is corrected by adding 0.001 to the hydrometer reading for every 3 degrees above 77 degrees Fahrenheit. For every 3 degrees below 77 degrees Fahrenheit, 0.001 is subtracted from the specific gravity reading. Some cell thermometers have a specific gravity correction scale opposite the temperature scale. The correction scale here is marked in thousandths. In this example, the electrolyte temperature is 68 degrees Fahrenheit. The correction factor for this temperature is about -3. So 0.003 is subtracted from the specific gravity reading of 1.222 for a corrected specific gravity of 1.219. This is the value that is recorded for the cell. After the specific gravity reading is taken, the electrolyte is returned to the same cell from which it was taken, and the specific gravity of the next cell can be taken. IEEE Standard 450 recommends checking pilot cell specific gravity once a month, and all cell specific gravities at least once per quarter. Specific gravity should be checked before water is added to a cell, because the water doesn't immediately mix with the electrolyte. Under normal float charge conditions, it may take 6 to 8 weeks for the water and electrolyte to thoroughly mix. In addition, specific gravity readings should not be taken during or immediately after a battery is given an equalizing charge. The reason is that it takes time for the sulfuric acid from the plates to mix with the electrolyte, so the specific gravity will continue to increase for a period of time after the cells have been fully charged. For this reason, specific gravity should not be checked until the battery has been on normal float charge for at least 72 hours after an equalizing charge. After cell specific gravities are corrected for temperature, they can be evaluated in several ways. One way is to identify the highest and lowest cell specific gravities and determine the difference between them. The difference is compared to high and low cell specific gravities from previous tests. A noticeable increase in the differences may mean an equalizing charge is needed to raise the specific gravity of the weaker cells. Specific gravity tests, if done at the right time and when properly corrected for temperature, give a good indication of the state of charge of the cells in a battery. All required safe working practices should be followed to the letter. For example, before beginning your work, remove all metal objects, including rings, metal watch bands, metal necklaces, dangling keys, and any other personal items that could cause a short. Even a single cell, if directly shorted, can melt a ring on a finger. Protective equipment should be worn, including a long-sleeved shirt, an acid-resistant apron, insulated acid-resistant gloves, safety glasses or goggles, a hard hat, and a face shield. Some companies also require the use of acid-resistant sleeve protectors and rubber-soled shoes or a rubber mat on the floor. Also, you must know where the eye wash station is located before you begin working, so you won't have to search for it if you need it. Cells that are cleaned with unauthorized cleaning solutions may exhibit crazing, which is cracks in the cell jar. Crazing results from the chemical reactions of certain cleaning solutions with the cell jar. IEEE Standard 450 also states that a cell voltage of 2.07 volts or below indicates internal cell problems and that the cell may need to be replaced. After cell-specific gravities are corrected for temperature, they can be evaluated in several ways. One way is to identify the highest and lowest cell-specific gravities and determine the difference between them. The difference is compared to high and low cell-specific gravities from previous tests. A noticeable increase in the differences may mean an equalizing charge is needed to raise the specific gravity of the weaker cells.